Hello. So, in this video, we're going to be introducing the idea of sort of tackling the derivative as a function rather than as a difference quotient at a point. So to motivate this, I sort of want to get across that this is in your own best interest, and really this is following sort of the number one rule of mathematicians, which is embrace laziness. I realize this might seem weird, but bear with me. Hopefully by the end here, you will agree with me. So our sort of overall goal here is to try to solve this problem, try to solve the underlying problem of this derivative bit like a mathematician would. So one of the mathematician credos is to solve problems in as much generality and as much abstraction as you can generally manage. The reason why mathematicians do this, I won't lie, first and foremost, we just think it's awesome and beautiful and we're nerds for it, so we do it because we love it. I realize that is a rather niche area, but really what we're trying to do, at least what we claim we're trying to do, is that we're trying to solve, to get at that sort of underlying structure and the heart of why something is true and how it works sort of at a fundamental level. Now, I realize you are not a research mathematician. You probably don't care what mathematicians think is beautiful. I get it. Nonetheless, I would argue that it's actually in your best interest to sort of use this approach really a lot of the time, but in this time in particular. So for no other reason than self-interest, this is worth sort of looking at beyond the fact that arguably it's an incredibly great thing on its own. So if we use the correct level of abstraction, which is a key word that I'm going to sort of bury because we're not going to go into incorrect levels at this point because I would love to. You don't want me to. So nonetheless, using the correct level of abstraction, it results in slightly more work up front, which we'll see, but massively less work later on. So really the mantra here, from your standpoint, work smarter, not harder, right? So how do we embrace laziness? So instead of solving derivatives at specific points, like, if you have a function and you want to know the instantaneous rate of change at -1, 0, and 1, let's say, instead of solving each of those things individually, we want to start solving these sort of limit forms, these difference quotients, in terms of a general point, x. Doing that is going to take marginally more work, admittedly. But as we'll see, the payoff, definitely worth it. So let's look at a sort of concrete example to see what I mean. So let's say we have a function f of x. We want to know what its derivative is at -1, 0, and 1. So we can do each of these things, right? And we'll actually do an example with a concrete f here in a second, but we could do each of these things. This one, then this one, and then this one. Or we could do it once in this, again, admittedly a little scarier, but more general format, and only go through this effort one time, okay? So let's do an example where we're looking at a function of f. In this case, f is x squared plus 3x minus 1. And we're going to plug in and sort of go down the rabbit hole with this very specific function using this sort of more general form, okay? So the first thing I do, right, I have the difference quotient. The first thing I do is plug in that definition of f. So I have the input, x plus delta x squared, plus 3 times the input, x plus delta x minus 1, and then I subtract just the function definition, x squared plus 3x minus 1, and that delta x is in the bottom. So remember, all of our sort of effort is keyed toward getting rid of that delta x in the bottom. That's almost always where the pain is, as it were. So the next step, we can't really do anything with how it is now, so the first thing I'm sort of going to do is just expand everything. My hope is that by expanding everything, I will be able to combine all my like terms and boil stuff down and eventually get rid of that delta x. So this first piece here, I have squared out x plus delta x. If you FOIL that out, you get the same thing. Over here, I distributed that 3, so it's 3 times x and 3 times delta x. Still got the -1, and this thing was already sort of nice as it was. Moving forward, distribute that negative on that second term over here, right? So I have negative x squared, negative 3x, and negative -1, so I get a +1. Then combine all the like terms together. So put all the x squareds together, all of the constants together, all of the something times delta x stuff together, all of that stuff go together, and this is what I end up with. Okay. Now, notice that I have a delta x in each of the top terms, and that's pretty important because that means I can factor out a delta x from the top. So now that we have, right, this factored out delta x, we can cancel the delta x in the top and bottom right there. So now we've actually gotten rid of that delta x in the bottom. So now we can actually evaluate this limit, right? There's nothing stopping us. So we can evaluate the limit and get to 2x plus 3. That is the end of the difference quotient. Now, it's worth a moment, right, to look at this, and this panel, this whole thing looks pretty intimidating, and it is pretty intimidating. Fair enough. The argument, though, is that you would have had to do almost this exact same thing with the concrete points, right? That -1, 0, and 1. So the jump in relative difficulty in computing this is sort of not as big as it might seem. It's non-trivial because delta x is maybe not familiar, but it's not as big as it might seem, and the payoff is going to be considerable. So let's see what that's like. So we've seen now that this difference quotient, we can boil it down at a generic x into 2x plus 3. That's what we just went through that whole big slide to see. But remember that this function, this 2x plus 3, represents the derivative of f of x at a point x for any input whatsoever, right? So if we want to actually figure out, say, what is the derivative at -1, well, we can just plug it in and compute, right? So we do 2 times -1 is -2, plus 3, +1. So this tells us, we can plug it in and get immediately what that derivative was at that point. Likewise at 0. Plug in 0, the derivative is 3. Plug in 1, derivative is 5, right? So now computing the derivative is incredibly fast. No effort, no need to go through all of that, big block of difference quotient again. So already I might argue that if you have to do a bunch of points, this is a much sort of more efficient use of your time and effort. But there's actually even more, right? So what happens if you want to know, well, where does the derivative equal 0? Now, on the one hand, if you're doing this with a difference quotient, you'd have to take that whole big difference quotient that represents the derivative, set it equal to 0, and solve with all kinds of, x's and delta x's or h's floating around, and it would be a big mess. It would be a lot of effort. It would be very unpleasant. But now that we have that function that represents derivative at any point x, we can just take that and set it equal to 0, right? So then we would subtract over the 3, divide by 2, we get that x is -3/2. So it allows us to sort of find where, the inputs that have some particular derivative value that we want, and it's much easier to do sort of that part of that rather than trying to deal with the difference quotient. And it turns out that we're going to be doing that a lot, by the way, so we'll see that when we get to applications. Now, it's worth a mention to sort of introduce or talk about sort of the conventional notation that's used for derivatives. So in general, when we solve for the derivative of a function f, we denote it as what we call f prime of x. So that's this piece here, that f tick parentheses x close parentheses. So that we say f prime of x. This is called prime notation. Another way you might see it is this df dx, and this is slightly different type of notation used in slightly different context. We're going to revisit this later, so I'm not going to jump into it too much here. You may have also seen it as dy dx, depending on if you've seen any calculus before, but the sort of important part about that notation is that it's a D on the top with the letter that is the function letter. So we had f, so it's df on the top. And then the bottom is d and the variable that you're taking a derivative with respect to. And we'll talk more about that a little later. But in this case, since it's a function of x, it's dx. Okay. And just so you see sort of how this works in general, derivative of function g, we would call g prime of x or dg dx. For h prime of x or dh dx. For r prime of x, dr dx, right? It's very formulaic. That's what we like with mathematicians. We're all about the formulaic or algorithmic naming. So this is sort of the conventional notation, the way you'll see this in a lot of texts and online and things like that. Okay, and moving forward in this class as well. So what do we do? So the derivative, we use sort of this, it's helpful to use this abstraction of the derivative, meaning like a derivative at a generic point, to represent derivatives at any value, right? We solve it in this sort of general case so that we can plug in whatever numbers we want and do so very quickly. But it also allows us to solve sort of lots and lots of inputs very, very quickly, rather than having to go through the difference quotient every single time. The other way we're going to use it a bunch is to let us solve for the inputs that have some desired output, right? So if we want to know where the derivative is 0, this is an easier way of doing that rather than trying to take the difference quotient and setting it equal 0. If we want to know where the derivative is 15 for some reason, right? Like, this is how we would do it. We'd solve the derivative part as an abstract function and then set it equal to. And the last thing, we sort of mentioned toward the end here is this conventional notation, the prime notation. So in general, if you have some function of x, then that function prime, right? So f of x, f prime of x, that's the derivative. Moving forward, we will also, again, talk about that like df dx bit, which is a slightly different way of looking at the derivative, but we'll tackle that when we get there. So it's worth knowing as they're used very interchangeably. So if you look up any other information, you will definitely see the df or dy dx notation a bunch. Just know that it's sort of the same idea, and we'll get into the nuances later. Okay, so that is that.